So what I'm going to do today is I'm going to talk about a story about how LinkedIn used RUM and POPs to make the site faster. And I cheated a little bit. I changed the title from the title in the velocity proposal, and you'll see why I did that soon. Okay, let's jump right into it. Again, but my Twitter handle is @Ritesh. In case we are not able to cover questions today for whatever reason we are run out of time, so feel free to reach out to me on Twitter. Right. This was 2013. This is how LinkedIn's performance looked like across the world. Green is good, red is bad, black is really, really bad. So as you can see, North America was pretty good. I mean, most of it is green. Europe was also decent, green, yellow. But we really were not doing well in South America. It is all orange and red. And we're really, really not doing well in Asia and Africa in 2013, right? Jump back to 2015 today. This is this is how the map looks like today. So let me just quickly do a back and forth. 2013, 2015, 2013, 2015, right? So as you can see, we improved a lot in Asia, and we improved a lot in South America. There's still work to do in Middle East and Africa, but we are going towards it. So in this talk, I'm going to tell you a story. The story has two main characters, Mr. Pop and Mr. Rum. Mr. Pop and Mr. Rum, they live in their own world. They don't talk to each other a lot usually. Rum is for measurement, Pop is for network optimization. Usually you don't see them together, right? So this is a story of how they came together, how they worked together to get us from 2013, the map in 2013 to 2015. This is the story in a nutshell. Let's not read through it, but the point I'm trying to make is I'll cover 5 major points, number 2 to number 6. There'll be lots of ups and downs in the story. There'll be a lot of roadblocks, and it's a bumpy ride. Okay. So let's jump right into it. Who here knows what is RUM? Raise your hand, please. Oh, cool, almost like 70% of you guys. So folks who didn't raise their hand, I hope you looked around because I'm not going to cover what is RUM. You'll have to talk to the people who raised their hand. Okay? Sorry, bad joke. I'll quickly cover RUM. It'll be a crash course. So, but yeah, RUM is a deep topic. RUM is an in-depth topic, and you should definitely go back and check it out, read about it. So, what is RUM? In one sentence, if I want to talk about what is RUM, I would describe it as client code to measure performance, right? Client-side code to measure performance. On web pages, that's usually JavaScript. In mobile apps, you can write your own code. You can write whatever you want. So that's basically it. Whatever code you write on your client side to measure performance from the client's perspective, that's RUM, right? Most of the times, RUM is based on navigation timing API, specifically for browsers. And LinkedIn is using open source awesome RUM library called Boomerang. Philip Tellis is somewhere here around here. Hat tip to him. So we are using Boomerang. It's open source. It's free to use. You guys can use it also. And RUM is how you get a map like that. Like RUM is how you know the performance of your app or your website across the world. You can get interesting metrics like DNS time, connection time, first byte download, page load, and so on. Right? This was your crash course on RUM. Sorry, I'm not going to go in more details, but that's good enough for us. That's good enough for our talk today. That's RUM. So what is POPs? How many people here know what is POPs? As I expected, very few. Thank you. Can you tell me the full form of POP?
Point of presence.
Point of presence, yes. POP is point of presence. Thank you. I don't know why it's called point of presence, but okay, whatever. But what it is, at a high level, it's just a small scale data center. You have big data centers, they are called data centers. The POPs are just small scale data centers, usually a rack, half a rack. You rent it somewhere in a co-location center. And And since they are small, they are cheap to build. And since they are cheap, you can actually build a lot of them. So you could actually have a global footprint using POPs. At LinkedIn, we use POPs to house our proxy servers, and that's all. We just use Apache Traffic Server as proxy servers. We put them in our POPs, and that's all we do for POPs, right? Okay, so that's POPs, and POPs are just proxy servers. Why would POP help in performance at all? Right, that's the next question. So let's take a simplified example of a world without POPs. Consider a user, let's say in India, talking to our data centers in US. This is a typical round trip latency, 250 milliseconds from India to US. So let's say a user in India trying to access www.linkedin.com, what will go through the wire, right? You will usually have one round trip for TCP connection time. This is a three-way TCP handshake, takes one round trip usually. So that's 250 milliseconds. Ignoring SSL handshake, that could take another 1 to 3 round trips, but let's ignore that for now. So once the TCP connection is established, the browser would send a HTTP GET request to the server, to our data center. Let's assume server computation time is 500 milliseconds. So data center gets the request, does its computation, tries to build the HTML page, and once the HTML page is ready, it'll try to send that data, send the whole HTML back to the browser, right? But here's the interesting point. Since the TCP connection between the browser and the data center is new, and the way TCP works is that it has something called congestion control. So it will not let you blast the pipe right away, right? There's limitations for new TCP connections. You can only send 15 kilobytes of data at a time. You can change that setting, but usually it's pretty low. So a typical LinkedIn page is 60 to 75 kilobytes of HTML. What that means is in a new TCP connection, that will take around 5 round trips, right? 5 round trips is 5 into 250 milliseconds, it's 1250 milliseconds. So if you add all this up, 250 plus 500 plus 1250, in this our toy example, the time it takes to download the HTML page is 2000 milliseconds or 2 seconds, right? So that's the world without POPs. Let's add a POP in between. Again, POPs are cheap, so you can add a lot of them. So you could probably push a POP closer to the user. So here, we put a POP 100 milliseconds away from the user. And again, between the user and the data center is still 250 milliseconds, right? So in this case, since POPs hold your TCP connection, the connection will be to the POP, and the connection time will reduce to 100 milliseconds only now, right? So there's a right away, there's a 150 millisecond gain by having a POP because it reduces your TCP connection time. Browser would send HTTP request to POP. POP would forward that HTTP request to data center. The interesting thing here is since POP and data center are both owned by us, the same company, the same entity, they're also talking to each other a lot all the time, right? Because they're serving users. The TCP congestion control windows between the POP and data center are usually huge, right? So POP data center takes its 500 millisecond and sends the data back to the POP. And since the POP and data center have a existing TCP connection, the congestion control windows are huge. You could probably be even 1 megabyte or 2 megabyte. A 70 KB HTML, will be transmitted right away in one round trip. You don't need multiple round trips between data center and POP. Okay. So that already is a saving. And then obviously between the POP and the browser, since it's a new TCP connection, you still have the same old problem of 15 KB at a time. You still go through 5 round trips, but since it's only 100 milliseconds now, the overall time spent is only 500 milliseconds. So if you add all this up, 100 plus 500 plus 500, it's 1100 milliseconds now. If you compare it with the world without POPs, it was 2000 milliseconds. So you already have a 900 millisecond gain right away. This is very huge because all you did was just put a proxy somewhere in a remote part of the world, and right away, all the users in that part of the world will have a huge gain. This is how I felt when I realized the full potential of POPs. This is how excited I was. Cool. So we know pops are awesome. Pops are great. Let's get into some nitty-gritty details. How are users assigned to pops? What are the mechanics? At LinkedIn, primarily we use third-party DNS services as our DNS authoritative servers. They serve www.linkedin.com, and they allow us to configure their services to give different IPs based on the user's location or based on the user's resolver location. So for example, if you can run this command right now. If you do this dig right now from here, you probably get our US West Coast IP address. This is our US West Coast POP. But if you run this other dig command, where it's using a resolver which is in Spain, you would get a different IP address. That is our Dublin POP address, right? Okay. So this is how we assign users to POP. Great. Now we know our DNS servers let us configure their services to give different IPs based on different settings, different location. You still have to decide what to configure there, right? You still have to decide, should users in India connect to a Singapore POP or Dublin POP? Like, what is a more optimal POP for a set of users? In other words, how to assure optimal POP assignment. Okay? There are two obvious ways to do that. You could do it based on geographical distance, that, hey, India is closer to Singapore, let's just assign it to Singapore. Spain is closer to Dublin, just assign it to Dublin. But that doesn't work because we know network distance is not equal to geographical distance. If you're trying to, for example, if you're trying to talk to a server which is like 1 mile away from you, the packets might actually take 100 miles or 200 miles, right? Geographical distance is not equal to network distance. You could also do it based on your knowledge of network connectivity. So the knowledge, when we build our Singapore POP, we were trying to figure out where should India go, right? And the normal knowledge in the community is that India connects better to Europe than India connects to Singapore. So maybe we should have sent India to Dublin. But again, this is all based on knowledge which can be outdated. Internet changes a lot. So again, this is also out of question for us. Can we make a more data-based decision instead? Instead of using intuition and knowledge, can we do a little bit more data-driven decision? We could use synthetic measurement. So there are companies like Keynote, Catchpoint out there. They have machines spread across the world, which they call agents. You can configure these machines, these agents, to run some test. So maybe you can configure them to download a small object from all your POPs, right? You can configure all the agents in India to download a small object from your Dublin and Singapore POP and compare the measurements, right? Whichever is the smallest, maybe that's a better POP. The problem with synthetic measurement is the agent distribution is not realistic across networks. So maybe your users in USA are mostly from Comcast, but Keynote has only one agent in Comcast. So that the distribution is not very realistic. Also, the distribution of connectivity is not realistic. Most of these agents are very well connected to the internet, but your users are not. Like, your users are connected to 3G, through DSL, through cable, through different connectivity platforms. So agent connected distribution is not realistic either. All right? So again, synthetic measurement is also not really good for us. So what should we do? If you see, I highlighted realistic here because we were trying to do realistic things. And if you remember RUM, RUM's full form is real user monitoring. So can we do RUM? Can we use RUM somehow, right? That was the question we're trying to answer. And it turns out we can. We can actually make our users as measurement agents. And if we end up using our users as measurement agents, then they will have a realistic distribution across networks. They'll have realistic connectivity distribution. And actually, there'll be millions and millions of data points, unlike synthetic measurement, where you probably get like hundreds of thousands of data points. So let's use RUM. How do we use RUM to solve this problem? We use RUM through beaconing. Beaconing is a common technique. A lot of people do it. The idea is you fetch a tiny object and measure the time. That's about it, right? You fetch a small object from somewhere and measure the time. So in this case, what we did was, for each candidate POP, let's say for India, we configured that our users in India, they will download a tiny object from Dublin POP and Singapore POP, right? And we will just time how much time it took to download that object. and we'll send that data back to our servers. Once we do that, we have interesting data now. We have millions of agents, as I was saying. You have your own real users as your agents doing your measurements. And then what you can do is you can analyze the heck out of that data to find very interesting data points, right? Very interesting opportunities of optimization. You can basically analyze the data to find what is the optimal POP per country. Is India better to go to Singapore overall or to Dublin? So let's look at some results. What we can do with this data? What we can do with this data is, let's say when we build a new POP, in this case, we build a new POP in Hong Kong. So we ran these experiments. We ran this experiment for all the countries in Asia, and here are some results. It turns out that for China, Hong Kong, the median time it took to download that small tiny object across all the users in China was 434 milliseconds, but Dublin was almost 1.2 seconds, and Singapore's was 500 milliseconds. So clearly, for China, Hong Kong is a better POP. Similarly, for India, when we did this measurement, turns out Singapore still remains the best choice. Singapore median download time was only 900 milliseconds, and Hong Kong was actually much worse. Dublin was a little bit better than that. Right? So again, using this data, we can now assign countries to new POPs. Whenever you build a new POP, you can figure out which country should be assigned to this POP. You can also audit current assignments. This is what we did. After we figured out this, we found that a bunch of our current assignments were actually not optimal. Specifically, I want to highlight this interesting scenario. India and Pakistan are neighboring countries. They are right next to each other. But for India, it turns out current POP was Singapore and optimal POP was also Singapore. But for Pakistan, for some reason, they have better connectivity to Dublin. So the optimal POP for Pakistan was Dublin. Similar cases here, we found that Brazil was assigned to a West Coast POP. That was a bad choice. We audited. We found out that we should be assigning them to the East Coast POP. This is a slide that makes me very happy. This is a result of all our hard work. Y-axis here is the percentage improvement in our homepage download time by doing this optimal POP assignment. X-axis is different countries. Dark blue is median improvement, and light blue is 90th percentile improvement in page download time. So as you can see, just by doing this, just by building new POPs and assigning the right countries to the right POP, we gained around 25 to 30% in India, 25% in Pakistan, Singapore, again, same range. And these are Russia and Brazil were cases where they were already close to POP, but just badly assigned. We did the audit, figured out Russia should go to Dublin and Brazil should go to our East Coast POP, and that already gave us around 10% improvement. Success, right? This is all. That's how it's done. Hey, go ahead.
So, two questions I have about this. One is, did you consider looking at the standard deviation of the numbers across multiple users? It's because if two numbers are very close to each other,
Mm-hmm.
it's more likely. And second, are you using just a JavaScript timer or resource timing to compare that?
So let me answer the first question. The first question is, did you look at some other metric, maybe standard deviation, because maybe this result, for example, this result gave you numbers which are very close to each other. If they are very close to each other, what would you do? I will come back to that later. There were cases where this happened, and we did some A/B testing, and I'll show how we did that. Second question was, were you just using timer for timing this, or were you using resource timing? We were just using timers, JavaScript timers. Sure.
Two questions. So, was there no GeoDNS variant for the DNS at all?
Was there, sorry?
When you moved away from using any GeoDNS service, you just went with the results of your RUM data?
No, so the question is, did you stop using GeoDNS? No, actually we did use DNS, but it's just that we figured out how to configure it using this data.
So you improved upon it?
Yes.
Okay. And did you do anything in the middle mile on top of it to accelerate that, or you just focused on the edge and progress?
The question is, did you do anything in the middle mile to accelerate that? No, we just focused on the edge. Middle mile was our own pipes, our own backbone pipes. It was already accelerated, so. Right. Success? No, it's not success. Obviously, it's not the end of it. We found that So in general, like my philosophy is that whenever you make major decisions, you should always verify. You should always verify what change you did, will it impact, did it actually take the impact that you expected it, right? So for example, like we decided India should go to Singapore, we should verify, is 100% of India still going to Singapore or not? How can you do that? Maybe we can use RUM to identify this. Like in general, can RUM identify which POP served a particular page view? Actually, that's pretty hard because RUM is client code, RUM is JavaScript. POP assignment happens through DNS, and browsers currently at least don't expose that information to JavaScript. Browsers don't let JavaScript know that, hey, given www.linkedin.com, what IP address would you actually point it to, right? So that's pretty tough, but we found a clever hack. We figured out that we own the servers, we own the POPs, so they can add a response header to the data that we want, and JavaScript can read that response header. Okay, and I'll go into details. So what we did basically was, after each page load, RUM would download a small object, again a tiny object, on www.linkedin.com/some object. And since www.linkedin.com would, with a very, very high probability, result in the same POP that was used for this page view, you could actually read this header that the POP would add. You could do your own headers, but we add a header called XLI POP, and the value of the header is the identification of the POP. So now we know which POP served this page view, and you can add this data and send it back to RUM, right? So what can you do with this? You can do interesting offline analysis. You can do the question we're trying to answer, like what % of traffic in India was actually going to the optimal POP, the Singapore POP, right? And you can do A/B testing, like to answer Philip's question. Now we know which POP a user went to. You could actually, at DNS, you could do A/B testing. 50% of the users in India should go to Dublin, 50% should go to Singapore, and evaluate their performance end to end. Right? So, so what did we find? What we found was not pleasant. What we found that assignment was far from optimal. We found that almost 31% of US traffic was being assigned to suboptimal POP. Specifically, almost half of the East Coast traffic was being assigned to our West Coast POP. Globally, the picture was not that bad. Only around 10% of traffic was getting assigned to suboptimal POP, but also that number is also pretty bad. So digging deeper, we tried to find out why it happens, and we found that this is an age-old problem. DNS-based POP assignment is usually suboptimal. And the reasons for that is assignment is based on the resolver IP, not the client IP. And here's an example of what that means. Let's say a user is in New York, right? And it took connection from Comcast as an ISP, and for some reason Comcast gave it a DNS resolver IP all the way in California. That resolver is in California, right? So what happens is our DNS servers will actually see this resolver IP and will figure out, okay, this guy is in California, so let me give it the POP, the US West Coast POP IP, even though the East Coast POP is much closer to the actual user. The other problem is think about how these DNS services actually figure out where the location of the user is, right? They use some database, they use some IP to geo databases, and those databases could be wrong. So what they do is, given this IP, look up which latitude, longitude is this IP on, and that's your location, right? But these databases can be wrong. They are actually known to be wrong. For example, you could actually have the resolver that the user is using is actually in New York, but the database says it's in California. So based on that, your DNS service will say, okay, you should probably go to the West Coast. Okay. So let's recap quickly. The story so far has been we started building POPs. POPs are awesome. We know POPs help in performance. We then use RUM to assign users to optimal POPs. We did the RUM beaconing. We figured out, given this country, what is the best POP to go to for this country. And then we hit a roadblock. We found that DNS-based assignment was not optimal, suboptimal. So how do we solve this problem? What is the accurate POP assignment solution, right? We could do a few things. We could bug our DNS providers that, hey, your assignment sucks, please help improve it. And we did that, and it helped a little bit. They upgraded their IP to geo databases, and it helped reduce the suboptimal assignment from 31% to 27%. But again, still 27% were suboptimally assigned. We could build our own DNS system. That will be the super awesome DNS system that can do assignment based on each user. We'll have all the information, and we can crunch the numbers and do the best assignment. Yes, we can do that, but it's a long-term project. It will take time. It will take a lot of time, a lot of infrastructure. We need it to solve this problem right away. So one of our network operation guys suggested, why not we use Anycast? How many people here know what is Anycast? All right, thanks. So I will go over what is Anycast because, yes, it's a little bit complex topic. What is Anycast? This is your 101. Anycast means you give the same IP, one IP, to multiple servers across the internet, right? This is as compared to the regular unicast world where you have one IP per server. This was what we were doing before. Each POP had its own unique IP address, and we are using DNS to route users. Now what you can do is you can actually configure all the POPs, POP A, POP B, POP C, to have the same IP address, 1.1.1.1. And Anycast would just work. Anycast is seamlessly supported at the routing layer. BGP, the routing engine of internet, supports it. And what Anycast does is it routes the packets to the closest server by number of hops. So in this case, you can see from Bob, POP B and POP C are actually 4 hops away, and POP A is only 3 hops away. So its packets will actually go to POP A. Right? So does it help? Does Anycast help? Yes, it probably will, because now the assignment is sort of based on client IP. Resolver IP is not at all used here, so we don't care what is the DNS resolver. It's all based on client. And there's no geo IP databases involved, right? Even if the databases are bad, doesn't matter, because BGP will take care of it. So Anycast is an interesting solution. We need to figure out how does it compare to DNS. Specifically, we want to find out, will Anycast send more users to optimal POP when you compare to the DNS, right? How do we do that? We say, let's test it. And how do we test it? We use RUM. So what you can do is, for each POP, this is in production. Production was still using unicast, so each POP was still using unicast. But we started announcing one more Anycast IP. This is IP address from all the POPs across the world, right? And then we configured a domain anycast ac.perf.linkedin.com to point to that IP, right? And then we did the same thing. We downloaded a tiny object and we read the header. We downloaded a tiny object on ac.perf.linkedin.com. This, for a given user, this domain will resolve to the POP which is closest in terms of number of hops for Anycast. That POP will fill up the XLI POP header with the right value, and RUM can read this back and send it back to your data center, right? So what it does is now we have data. We have 2 sets of data. One, now we have for each user, what is the Anycast POP that it will connect to if we are using Anycast. Given this experiment, we can now say for each user what is the best Anycast, what is actually Anycast POP, right? And from our previous experiments, we know for each user what is the optimal POP. So now we can compare these two and figure out whether Anycast wins or DNS wins. So here we did it. There are some nice results. Illinois, through DNS, through DNS, the percentage of optimal assignment was only 70%. Through Anycast, it jumped to 90%. Similarly, for Florida, Georgia, Pennsylvania, different states across the US, there was interesting improvement for optimal POP assignment. Of course, there is a plot twist. There were some cases where things were really, really, really bad. For example, Brazil, through DNS, was 88% optimal assignment before, but Anycast, it dropped to 33%. Similarly, Arizona, New York had the same issues, right? It's one of those days when you feel like nothing is going for you, right? This is how I felt when I figured that out, figured the problem. That's okay. Let's figure out what the problem is, let's dig deeper. When we dig deeper, we found out that Anycast does routing based on fewer number of hops, but fewer hops does not equals lower latency, right? So what can happen is your pop X, which is only 2 hops away, this hop could be an intercontinental link. It could be a 200 millisecond link. But for Anycast, it's the same thing. It's just 1 hop away, right? So even though the best pop for this user, Alice, is Z, but it's 3 hops away, so its packets will be actually sent to X. All right, so we know the problem. How do we solve it? We went back and figured out, hey, maybe DNS wasn't so bad, right? We found that the continent level identification from DNS was actually pretty good. If a DNS provider says this user is in Asia, there's a big chance that it's in Asia. If a DNS provider says this user is in North America, there's a 99% chance that this user actually is in North America, right? The bad assignment, the bad identification was at the state or city level. Right? So let's use this information. We used this information and came up with something we call regional Anycast. What it means is we will give one Anycast IP per continent, right? So this POP might be in Asia, and this might be an intercontinental link from a user in US. But now we'll give a different IP, 2.2.2.2, to all the POPs in Asia. And all the POPs in North America, Z and Y, will have the same IP address. This is interesting. This worked. We ran the similar RUM experiment, ac.perf, with this different configuration, and everything was better. Everything was good. Right? Here are some results. In December last year, we did this ramp in USA. Y-axis is the percentage of traffic going to the optimal POP. X-axis is just a date, and different lines are different states in US. Right? And as you can see, towards the right, everything goes up. All the states have better POP assignment, better percentage of optimal POP assignment using Anycast when we use the regional Anycast solution. Right now, we are evaluating Anycast for outside North America, and it's in progress. I'll definitely post something if something interesting comes up. But that worked, right? Sure.
On the previous slide, which were the ones that were back? There was Arizona or something like that.
Yeah. Sorry. So did it work? Is that the question you're asking? Damn it. Yeah. So sorry. I don't have the graph for that. So New York was in that graph. It worked. Arizona also was fine. It probably didn't improve by a lot, but it didn't get worse at least. And Brazil was, again, we didn't ramp Brazil on Anycast because we only did the USA ramp right now. So Brazil was 88%.
Okay, but still for all those other states, you saw the improvement.
Yes, we either saw improvement or we saw no change. It didn't degrade. Right, so let's recap again. What have we done till now? We built POPs, then we use RUM to assign users to the optimal POP, the best POP, but we found the DNS-based assignment was not optimal. So we evaluated Anycast as a solution. We found that global Anycast was not a good solution. So we came up with the regional Anycast solution, and now we are using Anycast to assign users to POP. Awesome. So we figured out the problem of how to assign users to the best POP. Let's build more POPs, right? POPs are awesome. Let's try to build more POPs. Yes, you can build more POPs, but there's a question: where should you build more POPs? Right? Where should you invest this money? Previously, we used to build POPs based on intuition or knowledge. Hey, our market is growing in Asia. Singapore looks like a good location. Let's build a POP in Singapore, right? No longer. We want to do, again, a data-driven methodology. So we figured out, can we use RUM data? Well, what we can do is probably we can take RUM data of historical RUM data, figure out this user was assigned to this POP and what was his performance. We can also go ahead and find a list of candidate POP locations. We did this, our network operations team did this, found a list of 400 facilities across the world. And we built a machine learning model that takes the historical RUM data, takes this list of candidate POP locations, and gives a score gives a score for each candidate location. So higher the score is, the better that location is for building the next POP. Right? I'm not going to go into details of the machine learning model, but it's a machine learning model. Everybody can do that. Everybody does that. There is another plot twist. So what we found that from the machine learning model is that it gave very close scores to two POPs, two locations, Miami and Sao Paulo. This is specifically for users in South America. We found that it gave very close scores, right? So how do we resolve this? How do we resolve this problem? We could do the same thing. We could maybe use RUM, fetch a tiny object, measure the latency, yada, yada, yada. But we don't have any servers there. These are candidate POP locations, right? These are locations where we are going to build POPs. So we don't have any servers right now there. But we found that our CDNs do, right? Akamai, Limelight, Level 3, all the big CDNs have servers across different POPs. So we pulled some strings, we talked to them, and we got IP addresses of CDNs in those locations. Then we configured a domain to point to those IPs, and we did the same thing. We fetched a tiny object over that domain and measured the time and reported back. Here's the result. As you can see, for Brazil, yes, Sao Paulo was the best POP location, yes, because it's in Brazil. Miami was close second, East Coast POP was third. But interestingly, for other countries in South America, like Colombia, Argentina, and Colombia is actually pretty north in South America, Colombia is north in South America, so Miami was better than Sao Paulo. But Argentina, which is very south in South America, even for that, Miami was a little bit better than Sao Paulo, right? Interesting result. We went back and talked to a network operations team. They talked to a bunch of folks and figured out that, hey, what happens is in Brazil, the networks in Brazil and networks in other South American countries, they don't pair with each other. They don't talk to each other a lot. And so their common pairing point ends up being Miami. And that's why Miami is usually a good location for most of the South American countries other than Brazil. So here's the recap of the story. Again, we build POPs, we use RUM to assign users to optimal POPs. DNS-based assignment was suboptimal. We used RUM and we found that we could gain LinkedIn download times by 10 to 25%. We found DNS-based assignment was suboptimal. In US, it was like 31% suboptimal. Then we evaluated Anycast as a solution using RUM. We found that global Anycast doesn't work. Regional Anycast is a good solution. And then we started using Anycast to actually assign users to POP in USA. And we actually saw the numbers drop from 30% of suboptimal assignment to 10%. And now we're using, now we're building new POP locations using RUM. So here's the end. Here's the learnings from this story. Use RUM. Use RUM to make your optimization decision. RUM is very powerful. You have client code in your hands. So you can actually make your clients, your users, do some of your work, right? Do it in a way that it doesn't impact their user experience. So maybe for web browsers, do it after page load, download a tiny object, don't download a 1 megabyte object. But you could use your clients as your measurement agents, and I highly encourage everyone to do that. You will make better decisions if you do this. Second, very important, trust but verify. Yes, we did the optimal assignment. We could have been happy that, okay, we did RUM, we used RUM to make optimal assignments. But if we didn't verify, we wouldn't have found that 30% of the users in America were badly assigned, right? So always trust but verify. And third, if you collaborate, you would get better results. You would make a bigger impact. Here, RUM used to live in its own world, only measurement. POP was its own world. Operation folks used to build POPs. We never talked. But what happened was one of the folks in operations, they came to us, said, hey, we are going to build this POP. Can you measure the improvement? That led to more meetings. And we had new ideas, and we collaborated, and we figured out we can actually use RUM to drive optimizations, right? So this is one of the big learnings. Get out of your silos, talk to other teams in your company. Maybe you'll hit something interesting. You'll find some interesting ways to collaborate, and you can have a bigger impact. I'll skip this because I think we are very close to out of time. And here's a picture of a duck and a cat together, working together, collaborating. And I'll take some questions for now. Thank you. Right? Any questions? Sure.
So you learned about RUM and you learned around TOPS and DNS-based mapping and all this kind of stuff. So I'm wondering, why do you do all this work if you could just ask one of your CDNs to do that for you? They've been dealing with these questions for many, many years and have solved them. And they've even solved the questions you're going to run into in the future. So I'm wondering, why did you make the decision to do it all by yourself instead of just telling someone to do it?
Good question. So the question is, why are you doing this all on your own? Why don't you use solutions that have been out there? CDNs do this all the time. There are a few reasons. One of the major ones is security. So if we were going to use CDNs to accelerate our dynamic content, we would need to give them our SSL cert, and that may not work for us. So that's potentially one of the major roadblocks. There were other reasons. They have solved all these problems, but they have solved it in a way that may not work for us. So that's why we're doing this. Any other questions? All right, thank you.